Evening, everyone, and welcome to the second talk of this particular course. And as discussed yesterday, Professor Kembhavi would be conducting today's session, and he will be talking more about what he spoke yesterday about binary stars, formation of stars, and so on. Yes, over to you, sir.
Thank you very much, Prachi. So, good afternoon, everyone. And let me begin where I stopped yesterday. So, we considered spectral classes, and then we said that there are these classes O, B, A, F, G, K, etc., which are made on the basis of the provenance of different kinds of absorption lines. And each one of these classes is divided into 10 subclasses. And then you define the classes with this kind of a description, but also mainly through giving examples. Certain stars of that kind are defined by experts. And when you want to understand, you want to see what the spectrum is like for that class, so you'd refer to the standard stars. And then there's something called a luminosity class, which I'll explain the significance to you in a moment. And then there are these 5 luminosity classes. And on the top, class 1 is the most luminous supergiants, and then you've got at the bottom the main sequence stars, which are called dwarfs. So just a word about how the spectra come about. As I've already mentioned to you, the energy generated deep down in the stars, to the center of the stars, and it travels forward. To most of the stellar interior, the temperature is so high that the gases are fully ionized. So there can be no absorption lines. But as you come closer to the surface, what is called the photosphere, so there the temperatures are low enough that the ionization is not complete. So you can have an atom in a certain state, the electrons in a certain state, and when a photon coming from the interior interacts with the atom, it could raise the electron to a higher level. And then when the electron descends back to its lower level, when you take it to a higher level, it has absorbed a photon. Okay, so that the absorbed energy, of course, gets thermalized in very different ways, but the photon is lost to the continuum spectrum. So you have such losses of photons wherever there are specific absorption lines in the atoms, and thereby you get the kind of spectrum that I've been describing to you. So the formation of the spectrum is extremely important. It's the theory behind it's called you need atomic physics, of course, quantum mechanics, and then you also need the theory of the stellar atmospheres. So we will not be doing much of that, but there'll be quite a lot of discussion over this course about the lines which are produced in the atmospheres of planets, of exoplanets, because we'll see that it is possible to observe these lines, and which will tell us a great deal about the exoplanets themselves. So I just would like to mention here that when you do all these calculations, when you want to say what is the strength of a particular emission line or absorption line, then the basis for all those calculations is a Saha ionization equation, which were derived by Saha in the early decades of the 20th century. And then it was one of the very important quantum mechanical derivations. And so it says that if you have got here a higher, for example, this is for nitrogen, let us say, then you say that the second ionized state of nitrogen to the first ionized state of nitrogen, or numbers in any state 2 or numbers in state 1 is equal to this particular expression, which depends upon the ionization potentials, it depends upon the temperature, it depends upon the electron density, and it depends upon these things which are the partition functions. So this is a very basic equation. Unfortunately, I have no time to go into the details of it. So now I come to an extremely important diagram for astronomy, which is known as the Hertzsprung-Russell diagram. It's possible that some of you are already aware of what the diagram is about. And all stellar theory, I've been mentioning to you about the equations which will govern the structure and evolution of a star. That stellar theory has got to be compared with the observed with the observed Husband-Russell diagram. So let us see what this plot is about. And I've taken this from a book which was written many years ago by Bini and Mihalas on on galactic astronomy. So you see here, so what you have here on the x-axis is the temperature, and then temperature on the y-axis you've got the absolute visual magnitude. So I told you yesterday what is the absolute magnitude. It's a logarithmic measure of the luminosity of the object. Okay, it is not directly log luminosity, but you'll need minus 2.5 log of f10, where f10 kpc is the f10 parsec, where f is the flux a particular star would have at a distance of 10 parsecs. And then you'll see each dot here actually corresponds to a star. And then, so for a given star, what you do is that you look at the class of the star, okay, and then you estimate the temperature. It is not always possible to determine the temperature very accurately. You can estimate the temperature in various ways. Even just given the class, you know roughly what is the temperature. But there are other ways also of measuring the effective temperature, right? So then first of all, you see that there are the discrete lines here. Oh my God. Please So, so these lines appear simply because of the discrete way in which the temperature is actually measured for it. I mean, they have no particular significance here. So you'll see that a vast majority of the stars are actually lying along a particular trajectory here. And because most of the stars are lying along this trajectory, it is known as the main sequence. Right. So let's see what happens on the main sequence. So if I pick a particular star here, then it has got a certain temperature, okay, and it has got a certain absolute magnitude. And then you see that as the temperature goes down, and let's see if I got here. Yes, you see, we saw this equation yesterday, which is simply the Stephen-Boltzmann law. So assuming that each star is a black body, then you've got the luminosity is equal to 4 pi r square sigma t to the 4. Okay, so you see here, as you go to lower temperatures, these are the inverse the temperatures higher to the left of the thing. As you go to the lower temperatures, you find that the absolute magnitude is actually increasing. So the temperature here decreases towards the right, and the absolute magnitude, the stars become brighter uh, up there. I mean, along the y-axis. So you see, as you go down the main sequence, the temperature is decreasing, and so is the luminosity of the stars. So now, a vast majority of them stars on the main sequence, but you find this bunch of stars here, and you call them giants. And there are stars here which are called supergiants, and there are stars here which are called white dwarfs. So now let us see why you would call these stars as giants. I mean, it's very interesting why they would call them giants, but it follows entirely from the Stephen-Boltzmann law. So you see here, and let us say stars which are at a temperature of about 5,000 Kelvin. Now all these stars have more or less the same temperature, so T is the same for them. But you see that as you go up from the main sequence to the giants, you find that the absolute magnitude has decreased quite a lot. Okay, so which would mean that the luminosity has increased. For a star compared to a giant star compared to a main sequence star, so you'll find that the temperature is the same, but the luminosity is much higher for the giants, and which would mean that the radius is much higher for the giants. So as you go, as you rise up from the main sequence, the radius of the star is increasing, and therefore you call these giants and called supergiants. And conversely, when you come to these stars which are known as white dwarfs, you will find there that for a given temperature, the white dwarfs have very small luminosity compared to the main sequence stars, which would mean that the radius is incredibly small. So in fact, when you actually end up measuring the radius of white dwarfs, you find that these white dwarfs have, while they have a mass close to the mass of the sun, the radius is about 100th smaller. So which would mean that their density would be a million times, it will be 10 to the 6 times larger. Okay, so this seems like a ridiculous situation, but which I'll come back to that if time permits at the end of my talk. Right, so so you see that we'll understand the main sequence as we go further into the lectures. And then what else can I say here? Okay, let me just show you the next one. So with this is annotated properly. So you'll see here that, one moment. You see here, this is known as the horizontal branch. These are the giants, the supergiants, the white dwarfs, and then you've got the temperature here, and in this particular diagram, you have got the things here, the stellar types here, and you can see that you are given the luminosity here. So stars here are 0.01, 1% of the luminosity of the sun. The stars here, the supergiants, have 10,000 times the luminosity of the sun. Okay, therefore the radii are very much larger. See that when this was discovered independently by Hertzsprung and Russell, I believe it was in the second decade of the 20th century. They had no idea whatsoever uh, as to why stars lie along the main sequence and why some stars are giants and some stars are supergiants. They had absolutely no idea. And in fact, right at that time, it was not even clear what is the material which makes up the stars, meaning is it a liquid or is it a gas? So you can see that in 100 years, amazing progress has been made in the understanding of the stellar structure. And this progress has been made because, first of all, first the quantum theory became known, and which is absolutely essential for the understanding of the stars. And then computational methods improved, and then of course computers become available, and all these, and then the theory was became quite well understood, and therefore it was possible to make detailed calculations and understand the main sequence. And this is just a beautiful picture of the main sequence taken from space observations. You see how many stars there are now. And in fact, every dot here, every dot here is a multiple number of stars. So blue, there's one star, and here the red ones are 20 stars and so forth. Okay, so now I'm ready to go into the equations of stars. I just put on just a couple of equations, and then I mean, if there is great interest in people, and if you would like me to amplify any of these considerations further, then what we could do is that we could during the month of February, and if some of you want to know more details about some of these things, then we could arrange one or two special lectures. Okay, or if you have, it will be very difficult for you to digest the material because I'm covering so much in just two lectures. But if you would like to have a session of question answers or some further explanations, I'll be able to glad to provide those outside the main schedule of this course. Okay, so the first one is hydrostatic equilibrium. And you see what important considerations, what important conclusions can be drawn from just these very simple considerations here. So you see that this spherical object that you see here is a star, and I consider a small element of gas in the star, and it has got mainly two forces acting on it. Okay, so so what are these forces? One, there is gravity acting on the small element, which will try to pull the element to the center of the star, right? And then there's a pressure which is acting on it, and you must understand that at every point the pressure is isotropic. I mean, you must have studied this in various places. So there will be a pressure which is pushing from below. There'll be pressure from the sides of the element, and there'll be downward pressure from above. But as it happens, you see that there is a small gradient from one side of the element from the lower side of the element to the upper side, and so therefore the pressure which is pushing it up is just a little bit more than the pressure which is pushing it down. And then, of course, so there will be a net pressure acting upwards. And then there is the force of gravity which is acting downwards. And then when you write down, and if the star is in equilibrium, hydrostatic equilibrium, then every element should remain in place. And therefore, you have, when you take that into account, you get this extremely simple equation that dP by dr, there is a pressure gradient. The pressure as a function of the radius is equal to minus gm rho by r square. And what is m? M is the mass of, not the mass of the entire star, but m is simply the mass which is, so I take the center of this element and draw a sphere around the center of the star, and it is a mass which is contained in that one. And that is because you know from Newton's theory that when you have perfect spherical symmetry, it's only the matter which is inside this sphere will attract it down. The matter outside does not have any gravitational force on it. I'm sure you have learned this in your classes. So this is called the equation of hydrostatic equilibrium. It is simple and elegant. The problem is that the number of variables in this equation is more than can be solved straight away. Because you see that you have got R is the independent variable. So you've got rho, which is the density of matter at that point, and you've got the pressure. So there are two unknowns here, and there is just one linear equation. And then, so how do we solve this? Not linear, only one first order equation. So how do you solve this? You need a relationship between pressure and density. And all of you know that that kind of a relationship can come from what is known as an equation of state. Okay, so now let us see. Now I'll quickly jump to a simple approximation of this equation. So the gradient dP by dr, if I just want an average value of it, I can take the pressure at the center, which is finite, and subtract from it the pressure at the surface, which is taken to be zero. So dP by dr is represented by Pc by r, where r is now the radius of the star. And that average density can be written as 3m, where m is now the total mass of the star. It will be m by 4 by 3 r cube. That's the average density. And then, so if I make this substitution in these equations, and then I'll get the central pressure is approximately equal to gm square by r to the 4. So you see how important this is. Yesterday I was asked, how would you know the conditions below the surface of the star? And what I'm giving you here is the pressure at the center, okay, in terms of the mass of the star and the radius of the star, both of which we can measure here sitting on the Earth. And then I told you that we need an equation of state and the perfect gas equation of state, which is uh, which is excellently applicable to a star because the temperature is very high, the matter is totally ionized, and the nuclei and electrons are just ideal point particles, and therefore the equation of state is P is equal to nkt, where k is Boltzmann's constant, and which is equal to rho kt by mp. So if I make these substitutions here in this part, then I get the central temperature is gmp by k by r. Okay, so and if I take values correspond to the sun, so what I do is that the mass of the star is normalized by the mass of the sun and the radius by the radius of the sun. So therefore, I can write this by introducing numerical values as 2 into 10 to the 7 into m by m solar upon r bar solar to the -1 Kelvin. So it's amazing. So now if I take m is equal to n solar, r is equal to r solar, what do I get? That the temperature at the center of the sun is about 20 million Kelvin. So if you do very exact calculations using the whole theory, and then you'll get that the temperature is more like 15 Kelvin. So you see that we have just jumped in 2 minutes from an obvious equation of hydrostatic equilibrium to estimating the temperature at the center of the sun. So now supposing I consider the temperature at the center of an object which has got a mass of 0.1 times the solar mass. So what would be the temperature at the center? It would be 2 million Kelvin. And 2 million Kelvin is about the limit for hydrogen fusion into helium. And that is why when the mass of the star goes below 0.08 solar masses or so, it is not possible to have fusion any longer. And therefore, you cannot have stars with smaller mass than about 0.08 solar masses. You remember I told you this yesterday. See how insightful just these hand-waving arguments can be. I will not go into the virial theorem. I don't have the time for it. And so let me look at the energy transport. So the way the energy is transported, I told you that there are two ways in which energy is transported in stars. So it is by radiative diffusion. So just imagine a photon, you have got all the nuclear processes going up, and therefore the matter is very hot, and there'll be photons which are emitted. So just imagine a photon which is emitted from the central region of the star. The photon will start traveling. I mean, it could be emitted in any direction. The whole thing is isotropic. Okay, but it quickly encounters an electron and it is scattered. How is it scattered? You can have Thomson scattering, which means there's no change in energy. You could have Compton scattering. So the electron is scattered, right? And then when the electron is scattered, it goes in some other direction, and then again it is scattered and goes in some other direction. And what we want to know is what is the mean free path, which means what is the average distance between two scatterings. So before I come to that, let us look at what would be the temperature gradient. So the temperature at the surface, as you know, is about 6,000 Kelvin. The temperature at the center is 20 million Kelvin. Okay, so you might imagine though that there must be a very great temperature gradient, but the fact is that the radius is 7 into 10 to the 5 kilometers. So when you take that vast radius into account, you find that the temperature gradient dt by dr, which is approximately equal to the central temperature divided by the radius of the star, and that is equal to 3 into 10 to the minus 4 Kelvin. So this is a tiny, tiny temperature gradient. I mean, this sort of a temperature gradient, you would not be able to actually measure in our vicinity at all. So for example, if I'm closer to my laptop, the temperature is a bit higher. If I move away, the temperature is lower. Okay, but look at the temperature gradient. That would be vastly more than the temperature gradient which you have inside the sun, right? So now the other measurement that we have is what is the mean free path? Means what is the if the photon is being scattered around by the electrons, so what would be the average distance it travels between two scatterings? Okay, so so you see that and that again I could derive this very easily for you, but the mean free path is approximately given by the mass of the proton in P into divided by the average density, and sigma T is a Thomson scattering cross section, which you know is 6.6 into 10 to the minus 25 centimeters square. Okay, so the density is about, I told you yesterday, just put the average density 1.4 grams per centimeter cube, and the mass of the electron is of the proton is 1.6 into 10 to the minus 24 grams. So you put all that in, and what you get is 1.8 centimeters. So which is much, much smaller than the solar radius, right? So therefore, so you have the mean free path, which is again extremely. So you've got a very small temperature, and you have got a very small mean free path, right? So you'll say, my God, the photons are not going to be able to move outwards at all. So how am I going to transport the energy? So the answer actually is very elegant, because you see, the temperature gradient is small, and therefore, but it is nevertheless there. And the photons, they keep diffusing, meaning that the photons get diverted from their direction, and then they go here, they go there. But just like you open a perfume bottle in a corner of the room, and then quite soon the perfume spreads all over. And that is known as the process of diffusion. So here, the repeated scattering of the photons, the short mean free path, okay, can be treated as a process of diffusion. And then you can write down the diffusion equation in one step. And then it turns out that when you apply it to the present case, then you get a beautiful expression for the average flux due to the temperature gradient. And then you see it is equal to 4AC. A is a constant related to sigma, the Stefan's constant. 4AC times T cube upon 3 kappa rho, where kappa is again the opacity which is related to the sigma T here, and then you got the density and dt by dr. Right, so you see the dt by dr, as you know, is negative, right? Because the temperature decreases outward. So dt by dr is negative. And so this negative, this minus sign and the negative temperature gradient together give you a flux. So I can, within the, I got the center of the sun, there's energy moving out. Anywhere inside the sun, I can draw a sphere. And because of the spherical symmetry, there'll be a net, there'll be a net radiative transport of energy. Why is it called radiative transport? Because the energy is being carried by the photons. So there's a net radiative transport outwards. And then I could come actually to the surface of the sun, and there I will get a flux which is coming out. And then I multiply that flux by 4 pi r square, where r is the radius of the sun, and I'll get the luminosity. And how much is the luminosity? It is 4 into 10 to the 33 ergs per second. So you see that this tiny temperature gradient, okay, and then this tiny mean free path together provide you the outwards transport of this stupendous amount of energy, 4 into 10 to the 33 ergs per second. So now it would be wonderful if that would be the end of energy transport, because we have got a nice equation and then we could play endlessly with it. But the physics is not so simple. So what actually happens is that as the temperature, I mean, you can imagine the situation. I told you that overall, the luminosity of a star depends upon power of its mass. The luminosity called m cube, m4, m5, depending upon which mass range you are in. Okay, we know that we are overall in the range of 0.1 to 100 or so solar masses, but depending upon where you are, the luminosity will be a function of m, like m cube, m4, m5, etc. So as I increase the mass, the luminosity will increase. Or if I say that if I increase, so the luminosity, so what happens when the luminosity is increased? So what you see that I need to transport more and more energy outside. And in order to transport more energy, you need to adjust the temperature gradient. Right? And the temperature gradient has to become high. And as the temperature becomes higher, you go into a completely new class of phenomenon. And what do you mean? How high is the temperature gradient to be? So it is, you see that it is dt by dr, the temperature gradient in the star. We put a minus sign here because then this becomes positive. If that is greater than the quantity which is known as the adiabatic temperature gradient, and which is equal to 1 minus 1 upon gamma. So gamma is just constant which comes in the adiabatic constant. For example, P goes as K to the rho to the gamma. Gamma is 5 by 3, 4 by 3, and so on. And then into T by P into dP by dr. So at any point in the star, so you look at the temperature gradient. And if that temperature gradient exceeds this quantity here, and then you say that the material of the star becomes unstable, unstable to convection, meaning that small little bits of the material they start moving up and down, okay, because there is instability. So we go back to this famous boiling water. So when you see when you are trying to make tea and the water starts boiling, you see the pressure, the bubbles coming up and bursting. So what happens is that a small little element, uh, a small little element, uh, which which a small little element starts traveling upwards because of the instability. As it goes to a higher level, uh, then you can see, you can imagine that the material, that the thing will start expanding. Why will it start expanding? You see, as you go upwards, the temperature decreases, and then the density decreases, and thereby the pressure also decreases. So I'm taking a small little element of matter from a lower level in the star, and I raise it up to a high level. So as it goes up, it is facing less and less pressure, and therefore the element must expand. You will agree with me. I mean, if you're live in front of me, I could have seen from your faces whether you understand this or not. Okay. So as you take a small little element and as you start moving up, it has to be in pressure equilibrium with the surroundings, and therefore it will start. Uh, so then it keeps expanding, and you can imagine that it expands to such an extent that it just becomes a part of its surroundings. But in the process, what has happened is that a hot element has gone up to the top, towards the upper layers of the star, and there it has, therefore, it has carried energy from the bottom to the top because it is hot and it cools as it goes up, and then it gives energy upwards. So, does this mean that energy from inside the mass, the matter from inside the star, is all going upwards? That is not true. As elements start going up, similarly, colder elements from the top, they come down. So there's an exchange of matter through the layers of the star. And in the process, energy is transported outside. And this is known as convection. And why is it so difficult to understand? That is because there's something called turbulence. See, when gas or liquid is flowing very smoothly, we have got all the beautiful equations of hydrodynamics which will apply. But the point is that turbulence is not smooth. Turbulence is disruptive. And I mean, there's all kinds of motion of stars and motion of the gas. And it's quite difficult to understand it. Well, so therefore, this theory was developed by Schwarzschild. Okay, so which Schwarzschild was it? It was the same Schwarzschild who first talked about black hole, the Schwarzschild radius of the black hole, Carl Schwarzschild. Uh, and he died when he was very young. He died on the battlefield in war. But before that, he had done all these marvelous astrophysics. Okay, so then, and I first understood this concept when I read a book written by Carl Schwarzschild's son, who was Martin Schwarzschild, and who was again very fine astrophysicist. I actually seen and met him and talked to him. So now the question is, we have got this. So I told you that there are two processes now. One is radiative diffusion, and the other is convection. And yesterday, I told you that when I first heard about this in my first year of college, so they said conduction, convection, and radiation. Out of that, we have covered two. What about the role of uh, conduction? There's other very beautiful thing. You see, here we are talking about the diffusion of electrons. And you look at the equation that we have got, and you got dt by dr. And supposing I put something constant capital K here, then what do you get? F is equal to minus K times dt by dr. And you'll remember that when you're trying to look at the conduction of heat in a bar, that is exactly the equation that you apply. Okay, you say that the heat flows according to the temperature gradient, and there's a constant. So if the two equations are the same, then the physics must be the same. So here you have got photons which are carrying the energy. In a bar, in an ion bar, the density is so high that the mean free path of photons is practically zero. So then what carries the energy there? It is the electrons which carry the energy. And then the physics is exactly the same. You can apply the diffusion equation and so therefore conduction is the same as radiative diffusion. So when you think about it like this, you see that it is far from being uninteresting. It is extremely interesting. And in fact, when you come to white dwarfs, because the matter there is degenerate, and all the lower energies things are filled, it turns out you can show quantum mechanically that electrons have got a much larger mean free path in white dwarfs. Therefore, conduction becomes an important conduction becomes important for the transport of energy in white dwarfs. All right. Now the last little bit here is energy generation. Physics there changes quite a lot. So do you have any questions at this stage?
So we have a few questions in the chat box.
Yes, please.
Okay, so we have a question by Shivam Tripathi, and he's asking, why is there an adiabatic constant in the temperature gradient equation?
Why you see, the point is that if you look at the equation here, so this is the equation of instability. Okay, and actually what happens is that what is the situation in which the element will start rising? So all the thermodynamics come into it. And so I suggest that you take a look at the derivation, and then you'll find that it comes in very naturally. Okay, then you'll find that, and then if you have further question about the derivation, please ask me.
Yeah. Maybe we can take one which is there before proceeding. So Gautam is asking that what will be the value of R and T for binary systems in the HR diagram? Should we consider the combined radius?
No, no, that's not true at all. Every point in the HR diagram is a star. So if you have got two stars in the binary system, okay, then they will have two representations in the HR diagram. So for example, I mean, and the two stars in the binary system can be completely different. Okay, they can both be the same kind of stars, or one can be a red giant and one can be a normal star. One can be a white dwarf or a neutron star, and the other can be a red giant. You could have binaries of white dwarfs. You could have binaries of neutron stars. I mean, everything that you could think of there. And in fact, LIGO, the gravitational wave detector LIGO, has detected a large number of binaries in which the companions are massive black holes, right? So, I mean, it's an extremely interesting thing about how you form these kind of systems. And the first of these systems were discovered when I was still a graduate student. And there's a very great Dutch astronomer called Van den Heuvel, and his specialty is that you give him any kind of binary and he can tell you how it is formed. Okay, so but the first explanation for the formation of these interesting binaries came from a graduate student, okay, a long time ago. Yeah. Any other question? No.
No,
All
sir.
right. All right. Then I come to energy generation and nucleosynthesis. Right. So you know that there was a lot of towards the end of the 19th century. There some facts about stars had become known, and it was then the question of how do you generate energy in the stars. So you see that I did not tell you about the virial theorem, but basically what happens is that how are stars formed? They are formed from diffuse gas. I told you yesterday, occasionally in some places in the galaxy, the density of gas becomes so large in some places that that ball of gas collapses under its own gravity. Okay, and as it collapses, it keeps the gravitational binding energy becomes more and more negative. Because you see that you know how much is the gravitational binding energy for self-gravitation, g m square minus g m square by r. So if I got a cloud of a certain mass collapsing, as r decreases, the gravitational energy becomes more negative. And then the energy which is released in the process, because energy must be conserved, half of the energy goes into heating up the object, and the rest of the energy is emitted to the external world. And so the object keeps getting hotter and hotter. So just imagine that I start with R almost infinitely large, then Gm square by R is 0. So then I come to a radius R where a star is formed. Okay, then the gravitational energy is minus Gm square by R, right? So then that much energy half that energy is gone into heating the star. So the sun, for example, I mean, you know how much energy is there in the sun because uh, because it is so hot. So it was proposed by Lord Kelvin that the sun just keeps losing the energy which it has acquired because the heat which has acquired during the collapse. So now we know the rate at which the sun is emitting energy, 4 into 10 to 33 ergs per second, and then we know how much gravitational binding energy is there, which is g m square by r. So if I ask you to quickly estimate gm square by r, how would you do it? Take m square which is 10 to the 66, and G is 10 to the minus 8. So that will give you how much? 10 to the 66, you get 10 to the 58, and then R is 10 to the 10. Okay, so that is so 10 R square is 10 to the 20, and so out of 58 you take out 20, and so so you see that you get a certain amount of energy which is there, and then you see at the rate at which you are expending energy, and then you find that the whole energy will be finished in about 1 billion years. But then what about the sun, which has got a temperature, which has got an age of 4.5 billion years? So clearly it turns out that the, the stored thermal energy is simply not enough to keep powering the star. And then as quantum mechanics and nuclear physics were developed during the first decade, 3 decades of the 20th century, then it was proposed that it is nuclear energy which powers the star. And then, so what is the thought here is that you see, if I take a nucleus of hydrogen, it is made up of 2 protons and 2 neutrons. So I can measure the mass of the 2 protons and the 2 neutrons, and then I can also measure the mass of the nucleus of the helium atom. And it turns out that the nucleus actually has got a lesser mass than the 2 protons and the 2 neutrons have in total. So what happened to the rest of the energy? What happened to the rest of the mass? That mass has been lost as energy. Okay, and so it would mean that if you want to disrupt helium nucleus and separate out the protons and neutrons, you need that much energy. You need that much energy to separate them. And what is the difference in the mass? And you can do the calculation quite easily, because if you just open your books on physics, you will get the masses of all the particles concerned. And then you will find that at the delta M, that is the reduction mass, is 4.76 into 10 to the minus 26 grams. Okay, so this much of mass has been lost in the formation of the helium nucleus. And how much does that energy correspond to? How much energy is that? And that delta E is equal to delta M times C square, and which
Prachi, we can't hear, sir.
Yeah. So maybe there is some problem with his internet. Let me call and check.
yeah. One moment.
So we can hear you.
Can you hear me now?
Yeah, yeah.
Okay. Right. So, so please tell me immediately if you can't hear me.
So slides need to be in the presentation mode, sir.
Yeah.
Yeah.
So the amount of mass lost in the formation of a helium nucleus is 4.76 into 10 to the minus 26 grams, which corresponds to an energy of 26.5 MeV. And how much is 1 electron volt? And all of you will know that 1 electron volt is equal to 1.6 10 to the minus 12 ergs. Right? So look at it in another way. So if I now I have, by bringing in these 4 particles, making the helium nucleus, I lost some mass, and therefore I have gained some energy. So what is the efficiency of the process? That can be put down as the fact you take the mass which is lost and divide it by the input mass. And how much is the input mass? 2 protons and 2 neutrons. And if you do that, so you will get an efficiency of 0.007. Okay, so which would mean that if you multiply by 100, you'll get 0.7% of the energy of the mass of the energy, because point is available. 0.7% of the mass gets converted to energy. Now let us do another calculation. So which you'll find here on the screen. One moment. To move this panel out. Yeah. So you see that the luminosity of the sun, you know very well what it is. Now, the luminosity of the sun will always come from this kind of a mass loss. So if I divide it by c square, this luminosity goes to the rate, the, the rate at which the sun is losing its mass. And that is equal to 4.3 to 10 to the 12 grams per second. And this is a great deal. You see, 10 to the 3 grams is a kg, 10 to the 3 kg is a ton. Okay, so you are losing mass at the rate of 4 billion tons per second. Okay, I mean, see, 1 ton is roughly the mass of an elephant. Okay, so like you can see that the mass of 4 billion elephants, okay, is being lost per second by the sun. And so what is the efficiency? So you see that is 0.007 into m solar, and so that is 1.5 delta. The delta m is zero point 0. The total mass which is lost. The total mass which is lost uh, will be 0.007 into solar mass is 1.4 to 10 to the 31 grams, right? So if you convert the whole of the sun, imagine that the sun is entirely made up of hydrogen, and then you convert the whole of it to helium. Okay, so then you will lose, then you will then you will lose so much mass. And so the total mass which you can lose divided by the rate at which you are losing mass gives you for how long the sun can continue to shine. And it turns out to be 10 to the 11 years. So you see that unlike Lord Kelvin's calculation, which give you about 1 million years or less for the lifetime of the sun, here we are getting 100 billion years. But the actual lifetime of the sun is much smaller than that. It's only about 10 to the 10 years. And that is because, first of all, the whole of the sun does not consist of hydrogen. About 25% of it is already helium, number one. And number two, not all of the hydrogen can be converted. And that is because only the mass which is of the center can be converted. Nevertheless, we already have a viable estimate. And therefore, we know that nuclear fusion indeed must be powering the sun. Now, going quickly through the concept of binding energy. So you find that, so we know that I told you what the binding energy per particle for helium. So we have got the binding energy here. For hydrogen, it is zero because it is just there is just one proton. You can have a neutron, and then you can have a helium atom where the binding energy is about 6.5 MeV, right? And then you can go on like that into all the heavier elements. So you see that it goes up and down. It doesn't go up smoothly. That is because as you keep increasing the number of nucleons, there's a certain rearrangement in the nucleus and the nucleon interactions and so forth. So the binding energy becomes a bit erratic. But what happens is that then you go on until you finally come to iron. And then when you come to iron, then the binding energy per particle, okay, per nucleon is actually decreasing. So what it means is that I can convert hydrogen to helium, helium to nitrogen, and so on until I come to iron. Once you come to iron, in order to make a heavier element out of iron, you will, because the binding energy as you go down decreases, you will go beyond decreases. So it means that you would actually require energy to go to higher elements. You will not gain energy. And therefore, if you say that stars keep making heavier elements, and once the inner part of the star is converted to iron, then there's a full stop. You can no longer generate any energy. But you can go from the heavier elements to lighter elements through the process of fission. And that is what happens when you split up a uranium, and then you get two lesser mass nuclei. So you go from there to there, and therefore you gain energy. So you see that this story is already here. Now, yield from nuclear fusion, that is when you go to helium, and then when you go at higher and higher, you can release at most about 8.5 MeV per nucleon, no more than that. Okay, is the most tightly bound nucleus, 8.8 MeV, that is iron 56. Elements heavier than iron can yield energy by nuclear fission. Okay, great, we use U-235. So now, just a mention here is that how do you bring the particles together? And when you want to bring the protons together, the protons are charged particles. Both are positively charged particles. So they'll be repelling each other. So as the photons come closer and closer, the potential becomes more and more positive. As a result of which, there'll be greater and greater repulsion. When they touch each other, the repulsion will be infinitely large. Then how do you bring them together into a helium nucleus? So that happens because as the protons come closer, very close, closer than 10 to the minus 13 centimeters. Okay, then the nuclear forces take over, and the nuclear forces are attractive. And the nuclear forces are far stronger than the repulsive electromagnetic Coulomb force. And therefore, therefore you can say that they'll attract each other. The problem is that for when you want to bring this Coulomb barrier, the electromagnetic barrier is very high. And in order to go over this barrier so that you can fall into the nuclear well, you require extraordinarily high energy. And that high energy is so that you need this barrier is about 1 MeV in height. And in order to exceed that energy, the temperature needed is about 10 to the 10th Kelvin. So which would mean, and what is the temperature in the sun? It is more like 10 to the 6 Kelvin. So therefore, if you go by this picture, then you'll never ever be able to have nuclear fusion in the sun. So how does the fusion occur? It occurs because of quantum mechanics. Okay, meaning that we know, and some of you would have studied it already, though not all of you, you'll definitely study it in your MSc, is that quantum mechanically, when you have got a barrier like this, classically you would not be able to, a proton sitting here, another proton comes from infinity and just goes back. So, or rather, it goes along a parabola or a hyperbola. But in quantum mechanically, there's a certain probability that you can you can penetrate through this barrier, right? And so that's the beautiful theory which was given by Hans Bethe and others. So when you want to convert hydrogen to helium, so basically what happens is that it is you can't just bring the four particles together because you see that the particles are all moving around because the star is hot, and the probability that two protons and two neutrons will come together is exceedingly small. They have to come together within a volume whose radius is 10 to the minus 13 centimeters. Right? And what is the probability? It turns out to be exceedingly and unacceptably small. And so therefore, then Hans Bethe worked out this proton-proton chain. So what happens is that you've got a proton and a proton coming together to produce what is known as H2. Okay, so deuterium. And then then this further reaction takes place, and finally H3, tritium, that gives you helium-4 and 2 protons. So the net result is that there are 6 protons on the left-hand side, 2 protons on the right-hand side, and these are, so the 4 particles go to the 4 particles of helium. But then you'll see that when these 2 protons are coming together, you get H2, but you get, and this nucleus of H2, what does it contain? It contains 1 proton and 1 neutron. So where did the neutron come from? It is because, so you have got this inverse beta decay which is taking place. Okay, and it is because of the inverse beta decay that you form a neutron. So you see that these are very complex processes, but they can be worked out in great detail. And you find that they are practically, in practice, they're able to generate the amount of energy that is required to power the sun. But there are also other processes which are known as the CNO cycle, for example, okay, which also generate, which involve the presence of higher elements, and but they can also go from 1, 2, 3, 4 protons, and the net result is that you get the helium nucleus, and then you have got carbon as an intermediary, and it is called the CNO cycle, but the carbon which goes in has come out here again. So it is like the catalysis of chemistry. So these are the 2 processes taking place to convert hydrogen to helium. And the nuclear physics is all extremely well worked out. And so you see what is the net result is that you've got these positrons which are going out, you've got the gamma rays which are going out, and you've got the neutrinos. So you should be able to detect the neutrinos. And until quite recently, the neutrinos it's not possible to detect them. And so there was doubt, there was a basic doubt in people's mind whether this whole story of nuclear fusion is true or not. Because now we have the capability of detecting neutrinos, but the number of neutrinos we detect coming from the sun is much smaller than what is expected if this conversion of hydrogen and helium to take place. The solution of that is known now, but again, I don't want to go into that at the present time. So you have to go beyond helium, and then so then you see that when you go beyond helium, you get hydrogen being converted. Converting going from helium to carbon requires a reaction which is known as triple alpha, and which was first considered by Hoyle, and he made a very important prediction. He said that if you want to convert helium to carbon, then the carbon nucleus must have a certain particular level, energy level, which at that time was not known. So this was the first successful physics prediction which came straight from astronomy. And Fred Hoyle was, of course, a very great astrophysicist. Right. So then, what happens is that in the Big Bang, and you have got about 73 or so percent of hydrogen, and then so 25% or so helium. I've forgotten the exact numbers which are produced, and then there are very trace amounts of some heavier elements. But when the stars start synthesizing the elements, you go from hydrogen to helium to carbon, nitrogen, and oxygen, and you go on and on and on until in principle you can come up to iron. And you come to iron only in the highest mass stars, but not in the sun will never go on to the stage of the sun will end its life once it has gone to the cyano part, carbon, nitrogen, and oxygen. So why? So then these are the abundances of the elements which are generated through the star. So there was a marvelous paper written by Burbidge, Fowler, and Hoyle. B square HF, Burbidge, Hoyle, and Fowler in 1957. So at that time, they were all fairly young people. And then they wrote this marvelous paper which worked out the entire nuclear physics of all these generations. But then you can't go beyond iron. So where do the heavier elements come from? So there are some elements which are formed during supernova explosions because the conditions there are conducive to the formation of the heavier elements. It was predicted that elements which are there and which are extremely important for sociological reasons on the earth, like gold and platinum. So it was thought that they will be formed only during the merger of neutron stars. But nobody had ever seen the merger of neutron stars. And finally, in 2017, a neutron star merger was detected by gravitational waves. It was observed in the electromagnetic bands and then it was found that indeed gold and platinum can be formed in these reactions. So that was a great triumph for gravitational wave theory. So you see that the amount of hydrogen which is produced is 0.627, helium is 0.36 to 0.3, and the heavier elements, which are all called the metals for historic reasons, is only just a few percent. All right. I'll now come to stellar structure. So now you see that I have shown you the Hertzsprung-Russell diagram, and then there are stars which are situated on the main sequence. So what are the characteristics of the main sequence stars? And we now know, how do we know that? Because we first had the Hertzsprung-Russell diagram, and then we constructed the equations which govern the theory of stars, and then those equations have to be solved, and then we get these insights. And then the main sequence stars, we know that they are homogeneous chemical composition. Okay, meaning that when a star is born, then it has got a certain chemical composition, and the stars burn hydrogen to helium. Burning is not really the correct word, but we colloquially say burning, but it is fusion of hydrogen to helium. And then now there's a vast amount of hydrogen in the star, but we know that it is burning at a certain rate. And so someday or the other, the hydrogen get depleted and the star must change its composition. Okay, so then, so the structure and evolution depend mainly on the mass and but also on the chemical composition. So as I had already mentioned yesterday, you give me the mass, I can tell you most of the properties of the stars. But the chemical composition is also, it all depends on the chemical composition, but much more so on the mass. Right. So when you take the equations and then you add to that the properties of matter, and when you solve them numerically, it's impossible to solve them analytically because they're so complicated. And then you solve them, and so then you see that you get curves like this. So what is this curve telling you? Is that you see that on the x-axis you've got small m by capital M. What do you mean by that? You see, you'd like to make a plot from the center of the star to outward, so R must change. But it turns out that it is much more convenient to have as your variable not R itself, but the mass which is inside R. So which is small m. So when R is equal to 0, the mass is equal to 0. As you move outwards, the for any given radius, you'll get a certain mass, and you use that mass as the variable. And when you reach the surface, okay, then you have reached the total mass. So m by m will be equal to 1. And then you see that how the density varies from you go to inside to the from the center to the outside. At the center, if you take a 1 solar mass star, at the center the density is about 100 grams. And when you come out to the surface, then obviously at the surface the density becomes 0, in a matter of speaking. With a 10 solar mass star, you find that the density is less actually. And now when you consider the temperature, its variation is much greater. Okay, so inside for a 10 solar mass star, the temperature inside is 10 raised to 7.5. Okay, but when you come to the surface, and then the temperature will be some 1000 degree Kelvin. Okay, so here you can actually, and you remember the main sequence, you have got the effective temperature on the x-axis and the luminosity on the y-axis, which is actually the absolute magnitude. And you see that you have produced beautifully the main sequence from the theory. Okay, and then, but this main sequence is a line. So where does the scatter come from? The scatter actually comes from the scatter comes from. You see that there's a scatter here, so it actually comes from the uh, the differences in chemical composition. And and so where do the red giants come from? And what happens there? Stellar evolution. So in order to understand where the giants come from, we need to go to stellar evolution. And what do you have there? You see that we have got nuclear fusion, so there's a change in chemical composition. And the change means that there is a evolution. And then the rate at which the chemical composition changes and the rate at which the evolution takes place is extremely slow, because we know that the total lifetime of the sun is going to about 10 to the 9 10 to the 9 years. Uh, and then so let us see how this slow but steady change takes place. So you see that when you've got a main sequence star, uh, it is characterized by the conversion of hydrogen to helium in the core. Why does that happen only in the core? And that is because it has got the core has got sufficiently high temperature for the fusion to take place. I've already explained the physical concepts. And then, when this is happening, it's called a main sequence star. But at the center, more and more of the hydrogen gets converted to helium. And here you have reached a stage where there is only helium at the center. So when most of the hydrogen here is converted to helium, then you no longer have the fusion taking place. And this is no longer production of energy. So the center actually begins to cool. When the center begins to cool, there are two important changes take place. One, the center begins to collapse. Why is it collapsing? Because you see that there's a pressure which is holding it up. But as the temperature goes down, the pressure decreases, and therefore it can no longer balance gravity. So the center will keep uh, contracting. And when the center keeps contracting, the outward layers are flung out, and they become So they become the outward layers. As they go out, they become cooler, and therefore the star actually becomes larger in size. And because they are becoming cooler, by the theory of the black body radiation, we know that the surface must become redder. So you are getting something like a red giant which is forming, right? And then the inside is collapsing if the total mass of the star is large enough, meaning that let us say it's about as much as the solar mass, then what happens is that as the center collapses, the temperature keeps increasing and reaches a temperature at which the helium is now converted to heavier elements. Then again the core becomes steady, the outward regions fall back, and then you've got a star with a new life. But it is no longer on the main sequence because you see that now you're converting helium to carbon, oxygen, and nitrogen, and that is where you get the scatter of the main sequence from. Then at some point the helium will get exhausted, and again there's a collapse, and again there's a expansion of the outer layers, and then in the center the conversion of heavy elements will start if the mass is large enough. And so this cycle just goes on and on and on. Okay, and then you see that if the mass of the star is large, meaning how much is it? About say more than about 10, 12 solar masses. Okay, then what will happen is that the eventually the center gets converted to iron. When it converted to iron, uh, and then there's no more conversion possible, and the center will collapse, and there's the end of the star. But the end of the star can also appear if the mass is small enough, can appear much earlier. And so when the end occurs, the outer thing goes, expands and just escapes in a giant explosion, and the inner parts form a white dwarf. So you see, you're moving out of the main sequence. When the hydrogen burning is completed, you get a red giant. Then again it contracts on helium burning, helium shell, again a red giant, carbon burning, carbon ignition. Right? This is the evolution of a high mass star. So now we come to gravitational collapse, meaning that depending on the mass of the star, at some point there's an uncontrolled implosion of the center. So when you got the implosion of the center, so what can you have as an end? First, let me go to the end product. So if the first of all, if the star is very low in mass, it forms a planet. If it is up to 0.08 solar masses, it forms a brown dwarf. I already explained that to you. If the mass is about 0.25 times the mass of the sun, then you form the helium, and that's the end of the story. You get a white dwarf at the center and a planetary nebula. For higher masses, again you get a carbon oxygen white dwarf, and then oxygen, nitrogen, magnesium white dwarf. But if the mass is more than about 12 solar masses, and then you get what is known as a supernova explosion, and at the center you will get a neutron star. If the mass is more than 40 solar masses, at the center you will get a black hole. And the outward parts you get a supernova explosion. These numbers are all approximate. Right, so here is the planetary nebula. It's a beautiful structure. It's a relatively low mass star has just exploded, and you get this ring-like structure. This is known as the ring nebula, and it expands. At the center of it, you've got a white dwarf. All right. So, what is a white dwarf? Now, let me take this very quickly. What's a white dwarf and what's a neutron star? So, you see that a white dwarf is a very compact object. And they were at the beginning of the 20th century, there were three white dwarfs which are known: 40 Eridani b, which was actually the first one, and then the most famous is the third white dwarf, and this is known as Sirius B. So, uh, so you see, this is the brightest star in the sky, which I mentioned yesterday, which is Sirius A. And then if you use good instrumentation and to look at it with high resolution, and then you find a tiny little thing here, which is called Sirius B. So what is Sirius B? As time went on, people derived the properties of Sirius B. And then what are the properties of Sirius B here? So you see that the mass, using Kepler's laws, and the Newton's laws, of course, they found that the mass of the object, the companion of Sirius B, was about 0.75 to 0.95 solar masses. These are old numbers. And then its luminosity was very much smaller than the luminosity of the sun. But the temperature of the surface was high. Because you see that as the luminosity decreases, you have seen from the Husband-Russell diagram that the temperature must be smaller. But here the temperature was high. It is called 8,000 Kelvin, and that is why it was called a white dwarf. And now if you put these together and use the Stephen-Boltzmann law, and then you get the radius of the object. And the radius of the object turns out to be a ridiculous 2 into 10 to the 4 kilometers. Actually, the radius is smaller than this, but at that time it was thought that it is 10 to the 4 kilometers. So you see, what the radius of the sun? 7 into 10 to the 5 kilometers. So this is so much smaller than the radius of the sun, but the mass is comparable to the radius of the sun. And so therefore, what is the density? 4.2 into 10 to the 4 grams per centimeter cube. Okay, so then 10 tons per centimeter cube. So you see that now you've got an amazing object, high temperature, and you believe it is gaseous, but the density is so high. And it was impossible to understand this kind of an object classically with the help of classical physics. And then we had to wait until the discovery of quantum mechanics to do that. Okay, so so what is the white dwarf? The thing here, and what is the physics of the white dwarf? One moment. So you see that I would have loved to derive this for you, the physics of a white dwarf. What actually happens is that because the density is so high, the electrons come extremely close to each other. And because the electrons come close to each other, then because of the Pauli exclusion principle springs into action, and therefore you can no longer treat it as a classical gas. So far, we have been treating that the gas in a star is a classical gas, which you can no longer do that. And when you apply the principles of quantum mechanics, then it turns out that you have to treat it as a degenerate gas. Okay, which means that the pressure is coming from the electrons. The pressure, you have to apply what is known as the Fermi-Dirac statistics, and the pressure is coming from, it is no longer dependent on the temperature. We have seen that for the ideal gas equation of state, P is equal to nkt. That no longer applies. And then it turns out that the pressure, the quantum mechanical pressure exerted by the electrons is so much higher. So in these calculations, you can assume for a moment that the temperature of the inner part of the star is zero. I mean, you know that it is billions of Kelvin, but because you are applying quantum mechanics, you can assume that the temperature is to be zero. And then you say that the matter is fully degenerate. And then the equation, the pressure comes from the degeneracy of the electrons. And that pressure is enough to hold the star. Because if you treat it classically, it would not be able to hold it. And then that is how a white dwarf is formed. And then, but people thought that all stars will end their life as white dwarf. But it was Subramanian Chandrasekhar, when we were 19 years old, and on the boat going to England from India, he did this calculation and he said that no, there's a maximum mass to the white dwarf. Okay, and if that maximum mass is given in terms of these fundamental constants. So this is considered to be one of the most beautiful relations in the whole of physics. Because on the left-hand side, you have got a quantity which pertains to stars and whose magnitude is like the mass of the sun. And on the right-hand side, you only have Planck's constant, the speed of light, the gravitational constant, and the mass of the proton. All four are fundamental constants. And this value turns out to be approximately 1.4 times the mass of the sun. So you can only have white dwarfs which can be smaller than this mass. So let's go back and understand the properties of the white dwarfs a little bit. It's very interesting. And so you've got 5,000 to 6,000 kilometers at the radius of a white dwarf. The inner part is degenerate. which means that the quantum mechanics rules, and the outer part, about 50 kilometers thick, is more classic. And then what is the size of the white dwarf? It is comparable to the size of the Earth. But the Earth has got a mass which is 3 billionths of the mass of the Sun. And so it would mean that the density of the white dwarf is very much higher. It's about 1 ton per centimeter cube. Okay, and then we'll see soon that there's something called a neutron star which comes in, and the neutron star has got a size of only 10 kilometers. And then if you get a black hole, then the size is absolutely zero. It's completely dark. So a white dwarf mass, okay, is about 1 ton per centimeter cube, and a relatively small elephant would have a mass of about 1 ton. So compress it to 1 centimeter, and then you will get 1 centimeter cube, and you will get the mass of the white dwarf. The neutron star is more spectacular because it has got again the size comparable, mass comparable to the mass of the sun, but whereas its radius is only 10 kilometers. So the density is 5 into 10 to the 14 grams per centimeter cube. So which would mean that put 1 gram of neutron star mass in one pan here, and all the 8 billion people now on the Earth in the other pan, and there would be their weight would be approximately the same. And a black hole, of course, the density goes to infinity, the mass is finite, radius is zero, density goes to infinity, and it constitutes what is known as a space-time singularity. Great. So now we come just 2 lines about a neutron star. So neutron star, when you exceed the Chandrasekhar mass, okay, but your mass is less than what is known as the Oppenheimer-Volkoff limit, which is about 2.5 times the mass of the sun. In that intermediate space, the object collapses to about 10 kilometers, and at the center you got the density of the matter there is comparable to the density of matter in the nucleus, atomic nucleus, and the outside gets thrown out in a giant explosion, which is known as a supernova. So this is the famous Crab Nebula, of which you must have seen pictures many times before. So the supernova occurred in 1054. We saw it occurring in 1054, occurred many years before that. And then it exploded, and you see this very beautiful picture, which is known as the supernova remnant. At the center, you got a neutron star, and the neutron star is a pulsar, which actually powers the supernova remnant. What happened? Yeah. So I've already told you already these things. And just like a white dwarf is supported by electron degeneracy pressure, so a neutron star is supported by neutron degeneracy pressure. And this is the structure of a neutron star. So you've got a fluid core. I mean, it's a quantum fluid actually, which is mainly made up of neutrons. You've got the solid crust here, and the total radius. The total radius is about 10 kilometers, 20 kilometers diameter for the neutron star. I won't go into these details. And when a neutron star is freshly formed, it has got a very large magnetic field, 10 to the 8 Gauss. Okay, and then it has got it spins very rapidly because of the conservation of angular momentum, and therefore it pulsates. Okay, in a very narrow beam, you will get is a beam of charged particles and radiation, and the neutron star goes round, and therefore you get a searchlight effect. If the beam of the neutron star happens to intersect your line of sight, that means intersect your telescope's line of sight, and then you could see it as a radio pulsar, or optical pulsar, or X-ray pulsar, and so forth. Right. But the last part to be covered in about 10 minutes is binary stars. So Prachik, I can go on for about 10 minutes more.
Hello, sir.
Can I go on for about 10 minutes more?
Yes, sure. Yeah.
Yeah. Okay. So now, are there any questions on what I have explained so far? Just a couple of questions. Prachi, are there any questions in the thing?
Yes, sir, we have a few questions. We have a question by Arpita Sahan. She is asking that, can you please explain a bit about homogeneous chemical composition of the main sequence stars?
Yeah, the homogeneous chemical composition only means that whatever that there's hydrogen, there's helium, and then the heavier elements, and the composition of the entire star is the same. So that is an important ingredient for the calculations.
So we have a question by Bruno, that why is the solid crust formed at the surface of the neutron star?
I see. So what happens is that you have got the neutrons on the inside. As you grow, as you go outwards, then you have the degeneracy is no longer complete. There are different processes which are taking place, and therefore, when I say it is a fluid, when I say it's a solid, you have to take those words with a pinch of salt. It only means that the equations of state which are governing them are different. Okay, the physics is incredibly complex.
Okay. So I would just request Arun S to unmute himself because he has a question which I'm not able to get here.
Yeah.
Yes,
Can you please quickly ask
Arun
for-
S, can you quickly unmute yourself and ask?
Shall we leave the question for later?
Yes, we can have it for a later.
Somewhere I heard that this type 1A supernova is occurring when the white dwarf accretion, I mean, when the white dwarf accretes mass from the binary star, when it reaches the mass of.
I get your question.
I don't know how a stable like this white dwarf can explode.
Yeah.
What's the mechanism behind?
Let me go through the binary stars, and if I get time, we'll answer it at the end. Okay. Yeah. Right. So now let's see what are binary stars. And here's a nice slide I made using pictures, of course, from Sky and Telescope. So all of you would have seen this thing which is known as the Big Dipper, Ursa Major in Sanskrit, and in the Indian languages you call it Saptarshi. And so there's this star here, which is known as Bizarre, which all of you would have seen. And then there's a very faint star there, which is called Alcor in Arabic, but which is in Sanskrit known as Arundhati. Okay, it's a faint star. You need to be able to detect it. And in fact, Vivekananda has also mentioned it in one of his lectures. Right? So now the question is, you could have two stars like this, which are very close to each other, but which are apparently, the Arundhati, for example, could be at a much greater distance from beyond Bizarre. Or Bizarre could be much at a greater distance than Arundhati. But simply because they happen to be along the line of sight, they may appear to be binaries. But this particular pair actually is a real binary. But it's a crazy kind of binary because the separation between them is very large. You see that the separation between the two is 1 to 1.5 light years. And it's even very difficult to establish that it's a binary. Okay, but the fun doesn't end there. You see that it turns out that this is a very interesting system because it was discovered, I think that in the beginning of the century, and it was discovered spectroscopically. I'll tell you what the meaning of that is. That Bizarre actually is a pair of stars. This is a much closer. Alcor is binary, but very far off. And Bizarre A, and there are two stars here called Bizarre A and B. Okay, which form a much closer binary system. And then it was discovered quite recently when somebody was trying to discover an exoplanet around Alcor, that it actually there is a Alcor itself is a binary. Okay, and it's a red dwarf. It's a very faint red dwarf. Okay, and then it was discovered that Bizarre A and B are both binaries. Okay, so you see that you start with Bizarre and Alcor, and now you know that there are 6 stars there. Okay, and each of these pairs is a real binary. It's quite amazing. Okay, so how do you define a binary star there? you define a binary as something, they have to be gravitationally bound, which means that they have to be going around each other. The total energy has got to be negative. So you can't separate them easily. And then they're just revolving around each other. And I already explained to you, already mentioned to you that a famous binary is Sirius B, which we subsequently got to know is a white dwarf. Okay, so you can imagine that the center of mass and Sirius A is going in an elliptical orbit around the center of mass, and Sirius B is also going around the elliptical orbit. Okay, and then you see you could sit on Sirius A, in which case you'll see that the white dwarf is going around it in an elliptical orbit. You could sit on the white dwarf and see Sirius A going around it and so forth. But they're only different. There are only different ways of looking at the whole thing. And what happens here when you actually you see here they're going around in ellipses. This is a view which is taken from top. Okay, so now just imagine. Sorry. Then you look at this binary, and the way it has been done, it is as if the plane of motion. You see that they'll be moving in a plane, as you can see very easily from the two-body problem. And then you see that here, in some sense, you're looking at it from the top, and that is why you see this elliptical motion. But just imagine you're looking at this binary from sideways. I mean, this binary is many light years away. You'll not be able to go there. But just like there are this binary which are looking at it from the top, there are binaries which are arbitrarily oriented so that you can look upon it sideways. If you look at the binary sideways, you see what happens here is that so here's a smaller star and a larger star. So you see that let's catch it here. The smaller star is going around, and when the smaller star eclipses the bigger star, so you get a dip here. And when the larger star eclipses the dip, you get a dip. The dip is shallower. So why do you think that is happening? And again, if you're live, I would ask you to try to answer that question. It is that the smaller star is actually much smaller. Therefore, it has got a lower temperature. So the amount of light that it obscures when it goes across the bigger star is less than the amount of light which is obscured, is greater than the amount of light which is obscured in the other possibility. Okay, so if you look at that carefully, you will find that one dip is shallower and the other dip is wider. So what is this known as? This is known as an eclipsing binary, and which is the same as the eclipses of the sun and the moon that you get. Okay, where the moon shadow, when the moon obscures the sun, you get a solar eclipse. When the sun obscures the moon, you get a lunar eclipse. Now, I showed you that when you look at it from the top, you will not get eclipses, but when you look at it from sideways, you'll get a full eclipse, but the inclination can be different, and so the star can only be partially eclipsing each other if the inclination is, say, 45 degrees. And how much inclination is permitted depends upon how big are the stars and from how far away you're looking at it. Okay, so please understand that many of the binaries that you see are so far away that you can't resolve the binaries. Okay, what do you mean by that? Even if you use a very powerful telescope, you can't see the binaries as two separate stars. Then how do we know that it's a binary system? So that is because as the eclipses take place, there'll be a change in the intensity. So if you look at a star and you see that the intensity is changing, then does it mean that it is always a binary system? That is not true. Because what can happen is that there are this intensity, a single star can also pulsate. You've got pulsating stars. So the star becomes bigger and smaller, and so the intensity changes. Except that the physics of pulsations is such that the pattern in the change of intensity is different for pulsating stars and is different from eclipsing binary stars. So it is from the nature of the eclipses that you see that you can conclude what is the situation. Right? And then you get something which is known as a spectroscopic binary. So what happens in a spectroscopic binary is that you actually can measure the spectra. I told you at length about the spectra of stars. And so the spectrum will have certain wavelengths in them. But these are not resolved. But when you keep looking at the spectrum, you see that the spectrum keeps changing. And why does the spectrum keep changing? You look at this here. In this configuration, both stars are moving perpendicular to line of sight. In this configuration, B is moving towards it. In the next configuration, B is moving away from it. So when the star is moving towards you, all the wavelengths will get blue shifted because of the Doppler effect. When the star is moving away from you, the wavelengths get red shifted because of the Doppler effect. So if you look at the absorption lines, and you will find that the wavelengths keep changing. And first of all, there will be two sets of absorption lines because there are two stars there. And in addition to that, the wavelength of the lines will be shifting in a certain pattern. So if you discover this change in the wavelengths, but you can't see the stars apart, and then you can call it a spectroscopic binary. And in fact, it turns out Sirius B, that I told you that bizarre A and B, there were two stars there, and that binary was discovered by a famous astronomer called Pickering from Harvard Observatory, who saw that it was a spectroscopic binary. I believe that it was the first spectroscopic binary to be discovered. So why is it so important for me to mention it, even though I have gone beyond my time? So that is because when an exoplanet goes across, when the exoplanet is orbiting its star, then it is possible for the exoplanet to actually produce an eclipse, right? And then you'll see that, but that eclipse is going to be very, very tiny, meaning that the size of the exoplanet is so much smaller than the size of the star. So it is like, I don't know how many of you have seen the Mercury or Venus going across the face of the sun. It's called an occultation. And then you'll see, what is it called? This particular name given that escapes me for a moment. And when you see that, you'll see this beautiful tiny dot moving across the face of the sun. But if the sun was so far away that I cannot resolve the picture, I cannot resolve the face of the sun, in which case when the tiny dot moves across it, there'll be a tiny change in the intensity of the observed intensity of the sun. And that is one way of discovering planets. So whereas if a planet, you can have the spectroscopic thing, where the planet is not emitting its own radiation, let us say, like a star. But because the planet is going down the star is also going down the planet. They're both going down the center of mass, if you look at it that way. And then the wavelengths of the spectrum from the star will be changing. Also, you will learn that as the light of the star passes through the atmosphere of the planet, then you can see what is known as a transmission spectrum. And that is another great field of study. So these are all details about the two-body things about the binary system, etc. I don't have time to go through it, and I will stop here because I conveyed to you what are the most important elements of binary stars, which is useful for the study of exoplanets. I'll stop here. If there are one or two questions, I can answer them. It's already quite late. But if you like, as I said, I can come on again and I'll do it. So just give me one moment. There's an important call coming in here.
Sure, sir.
Yeah, Girish. No, I'm in a lecture which is going to end in about 5 minutes. I'll get back to you. Okay. Bye. Yeah.
Yeah, thank you so much, sir. It was really a wonderful session with a lot of interesting animations and all of that. Thank you so much, sir. So we have one question. Mostly all the others are answered during your presentation. So why can't we have a question by Sri Krishna Anand, and he's asking that why can't we observe the spectrum of eclipsing binaries and detect them? Is the Doppler shift too small to measure?
Yeah, this is a very good question. You can detect. You can also you can have a binary which is both eclipsing and spectroscopic, and that is fantastic. Okay, because you see, as I told you that in order to, you have to get all the inclinations right and everything has to be right. But when it's an eclipsing as well as spectroscopic binary, then it helps you very much in measuring the masses of the components. So you've got every kind of variation that you want in astronomy.
Yeah, thank you. So thank you so much, sir. Many of the participants are asking that, will the presentation be shared and so on. So we just for the participants that we will be asking the speakers or taking consent from them, and at the end of the course we will be sharing the resource material and presentations, etc.
So the next lecture will be by Ravi, and just as I have introduced you to the physics of stars, he'll introduce you to some important elements of the study of exoplanets, right? And then just how do you discover exoplanets and so forth. So that will wind up the first part of the course, and after that you will get these 10 different speakers.
Yes. So we will be meeting again tomorrow, same time, 4:30, for the next session, as sir mentioned by Dr. Ravi tomorrow.
Ravi, would you like to say something?
No, it's just that tomorrow we'll give introduction to exoplanet detection techniques and the history of exoplanet detections that have happened over the years, and some statistics of where we stand right now regarding the exoplanets. There's a question in the chat about more elaborate sessions on stellar physics in the future.
Yeah, that can be done. So let's see what other people say. And we'll try to arrange 1 or 2 more lectures. You'll have to tell me what you want, because otherwise it'll be a 40 lecture course.
Yes.
All right then. Bye. Thank you very much. Thank you very much, Prachi and Gayatri and others for conducting the session. Yeah.
Thank you so much, sir. Thank you, everyone. Let's meet tomorrow again, same time. Thanks. I'll end the meeting now.